We're going to take a look at chapter 15 today, solutions. Characterize what a solution is, how to quantify solutions. That's in fact even more important. And then how to manipulate them to our advantage. That's basically dilutions and stoichiometry. When we have a balanced chemical equation, sometimes the reactants are in solution. And of course, I need to define what that is. What is a solution? A solution is a mixture. In other words, the components of a solution can be separated physically, as you don't have to invoke chemical means to separate the components, such as you can distill the components away from each other. You can just evaporate one of them if the other one is non-volatile. Sometimes it takes a little more effort, a little more exotic techniques like chromatography to separate them. But sometimes you don't want to separate. They're in this mixture for a purpose. And recall what a homogeneous mixture is. Everywhere you look in that solution, in that mixture, you get the same ratio of components. Exactly the same everywhere. That's homogeneous. Now, for solutions, our terminology is such that there's only one solvent, and the solvent is the major component, such as when we say aqueous solution, we mean water is the solvent, and everything else is a solute. You can only have one solute, but you can have as many solutes as you want or as you need. And the solutes are usually the minor component. There are exceptions. For instance, sugar water. When you mix up sugar water for your hummingbird feeder, you start off with a certain amount of water and then some sugar. I usually do 50-50 volume ratio. But you can start off with just a little bit of sugar and it'll go into solution, it'll dissolve. Then you can add more and add more. In fact, that's one of those components where you can start off with a smaller amount of solute, that is the sugar, and eventually you can end up with more solute than you do solid. It's just that soluble. So by convention, the one we start with as a solute stays a solute no matter what the concentration is. And I just referenced aqueous solutions. That's simply solutions that have water as the solvent. Now we generally think of the liquid solvent and a solid solute. And that's one type of solution. But based on our definition of homogeneous mixtures, we can have any type of phase mixed together and make a homogeneous mixture. For instance, the air we breathe is a homogeneous mixture. It is a solution of primarily nitrogen and oxygen. But there are some other minor components like argon is about 1%. And then other things like carbon dioxide and various other trace gases. But that is a solution. Right? The solvent is a gas, the solute is a gas, and the solution, the phase of the solution itself is a gas. Now, one thing about gases is if you mix two or more gases together, you always get a solution. Every time. There's no such thing as a heterogeneous gas mixture. Other types, we can mix two liquids together. Like alcoholic beverages are that way. Ethanol is a liquid, water is a liquid, and various other components are primarily liquids, except for things like sparkling wine and champagne. They have gases mixed in with them. So that's a combination of a gas, let's see, yeah, a gas and a liquid here, carbonated soda. You can mix a gas and a liquid. You can actually have solid in a solid. Brass is an example. Brass is a solution of primarily copper as the solvent and nickel as the solute. But how you get there is kind of tricky. You have to heat them up and melt them first before they'll mix. But once they reach room temperature again, solidify, now you have a solid solution. This is the typical one, the one we normally think of as a solid dissolved in a liquid. Sugar solution, seawater is a solution of many different solutes in that solvent. Some types of solutes remain intact when they go into solution, and table sugar is one of those examples. The molecule does not break up. The whole molecule goes into solution and becomes homogeneously mixed with water. But ionic compounds, when they go into solution, they break up into individual ions. Sodium chloride is an example of that. So when you put sodium chloride in aqueous solution, it breaks up into sodium cations and chloride anions. So what is it about the solute and solvent interaction that forms a solution? For ionic substances, they take advantage, right? You end up with this, that. They take advantage of the interaction of electrostatic charges. Electrostatic interactions cause positives to attract negatives. So when sodium is in aqueous solution, it is surrounded by water molecules. Like that. And chlorine is also surrounded by water molecules. But the one thing that's obvious here is that water is not charged. Water doesn't have a negative or a positive charge in this sense, where you have a complete transfer of electrons either to an atom or away from an atom to make a charged ion. But you still have electrostatic interactions. And the reason for that is that water is what we call a polar molecule. In other words, the water molecule has polar bonds. In other words, the electrons like to spend more time around oxygen than they do around hydrogen. It's a slight shift of electron density toward the oxygen. Okay, so that gives this side of the molecule a slight negative charge, and that's what that small Greek letter delta with a negative charge means, slight charge. It's not a complete charge like this. The electrons are not completely transferred. And that means that this end of the molecule becomes positive. So once you realize this, you can see why this part of the oxygen of the water molecule is oriented toward positive sodium because it's slightly negative. And that interaction is what brings sodium into solution and chloride into solution based upon this slight positive interaction with the chloride. And this is what it would look like on the atomic scale, where the water molecules come in and the positives attack the negatives, the chlorides. And once you get enough of those water molecules around this chloride, they will start to pull because they're also being attracted to water molecules that are not directly in contact with the chloride. So you got water molecules out here also pulling on it, and that force adds up. And eventually it pulls the chloride out of the crystal. Similarly, the sodium will be attacked in that manner, and it will also be pulled out. So there's your chloride, and there's your sodium surrounded with water, and that's called hydration. And that's what brings this ionic solid into solution. Now here we talked about the polarity of the whole molecule, which is true. Taken all together, the polarity of that molecule is toward the oxygen. It's a polar molecule. But some molecules have parts of themselves that are polar and the rest is nonpolar. In other words, you don't get an uneven distribution of electric charge so much around this side of the molecule as you do around this side. So when this type of molecule goes into solution, the interaction with water is with this end of the molecule where that polar bond exists. This molecule is ethanol, the drinking kind of alcohol. And the water associates itself with this hydrogen. And there's some hydrogens from the water molecule that will also associate with that oxygen. It's still electrostatic. And that's what allows a high percentage of ethanol to go into solution, is that interaction. This is, you don't have to memorize this, it's just for illustration. This is the geometric structure of sucrose, table sugar. And one thing you'll notice is all of these OH bonds, all these OH groups scattered all over the molecule. Just like that ethanol, they are polar sections of the molecule. So water will interact here. It'll interact here, here, here. Everywhere there's an OH, you get interaction with water, attraction to water. And that's why so much sugar will go into solution, because the attraction is very strong. Now, the flip side of that coin is that nonpolar molecules are not attracted to water because they don't have uneven distribution of electrons. It doesn't give them a slight charge. Oil is an example. Oil is just a long string of carbons bound together. You'll see here in the center, those are your carbons. And each of the oils vary by how many carbons there are. And then each carbon has around it hydrogens, right, all the way around. the electron density is equally distributed all over that molecule, right? It has no slight negative charge, at least not a permanent one. So it doesn't interact with water. And that's why when you mix up your salad dressing, if you make your own salad dressing, put oil and vinegar together and then maybe some spices and shake it up real hard and put it on your salad real quick before it separates. Okay, there's a term here that I think we didn't define earlier. Hydrogen bond. The hydrogen bond, let's use our ethanol, for example. Let's see. Like that. There we go. Okay, so for ethanol, you have this OH group on the end. And the density of electrons moves toward the oxygen. So we get a slight positive charge here and a slight negative charge there. When these, and this is a very polar bond, we say, because the shift of electron density is greater than most. And when you put these two together, if it's just pure ethanol, then the molecules will interact and you'll have, and then the rest of the molecule out there. And what will happen is you'll get an interaction here, or you'll get an interaction here. And that represents not a complete bond, but a partial bond. And this is called a hydrogen bond. It always forms when you have hydrogen bonded to either oxygen or fluorine or even nitrogen. And it's a very strong bond. And it's not as strong as these bonds right here, but it's very strong interaction between molecules. And it's characteristic of anything that bonds with water, anything that goes into solution with water. Takes advantage of that hydrogen bonding if it's non-ionic. If it's ionic, then you get a polar ionic interaction. But if it's a non-ionic molecule, then there's potential for the hydrogen bonding. Okay, so how is a solution made on the molecular level? It actually occurs in two steps. Now, I'm not sure this slide will adequately explain it. Let me check my hard copy. And we'll look ahead just a step or two. Okay, I'm going to elaborate on this slide. When you get the solution formation, can be visualized in 3 steps. And these all occur pretty much simultaneously. The first thing that has to happen is you have to break apart the solute. In other words, in a pure solute, you'll have interactions that hold it together, such as sodium chloride, very strong electrostatic interactions in that solid crystal matrix. And you have to add energy. This requires an input of energy. Okay? Then you have to also break apart the solvent, particularly for things like aqueous solvents. The aqueous solvent, where you have the interaction of the hydrogen and oxygens holding it together. There is strong bonds. So this also requires an input of energy. Okay? Then after you've done that, and this part right here is what they call make a hole. This right here is make a hole. That is some place for this molecule to go, gives it a place to go. Then when it goes in that hole and interacts with the solvent, then you form the solute solvent bond. And this one is input release. That one releases energy. Okay, so this in these three steps, you got to break the solute apart, you got to break the solvent apart, and then you put the two together. Energy goes in, you get some energy back. Now the balance between putting energy in and getting energy back determines whether your solution will get hot or get cold to the touch when it forms. If you put a lot of energy in, but you don't get much of it back, your solution will get cold. But if you put energy in and you get a lot of back, your solution will get warm. And that's the basis for marketing cold packs and hot packs in the hospital environment. If you've ever seen those packs, they're like plastic bags filled with water, actually, and then there's a capsule inside, and it's got a solid solute. And when you break it and mix it up, it goes into solution, and one of them gives off heat, and the other one absorbs heat. So you got the difference between hot pack and cold pack. Now, there are different chemicals in those capsules. They have to be to provide the proper balance in these three steps to either give you heat or take heat away. Okay. This is our rule of thumb. Like dissolves like. What do we mean by like? Well, we're actually talking about polarity. Polar molecules as solutes dissolve better in polar solvents. So sugar, alcohol, ionic solids like sodium chloride, they are considered polar, or actually ionic or polar, and they dissolve well in polar solvent like water. But if your solvent is oil, then sodium chloride, sugar, alcohol will not go into that matrix. They don't like each other. So like dissolves like means it's based upon polarity. So polar dissolves polar, nonpolar dissolves nonpolar. Which of the following solutes would generally not dissolve in a specified solvent? Oh, we're going to assume everything's in the liquid state. All right, so how about carbon tetrachloride mixed with water? you have to understand something about the structure of the molecule. So when we say this one, carbon tetrachloride in water, well, we know water is polar, but what do we know about carbon tetrachloride? Carbon tetrachloride is non-polar. The structure of the molecule puts carbon in the middle, a chlorine here, a chlorine there, a chlorine there, and in the back, another chlorine. That's what's known as a tetrahedral structure. The points here, these chlorines, they occupy the apexes, the points of a tetrahedron. A tetrahedron is if you've had geometry, you know what it is. But it's a triangular-based pyramid. And they're all equilaterals. So they're equally spaced. And any polarity that could develop here, which might develop, for instance, between carbon and chlorine, like that, since they're equally spaced, they cancel one another out. So that molecule is non-polar. Right? So it will not form a solution. We used to use carbon tetrachloride in the dry cleaning industry. In other words, you send your favorite wool outfit to the dry cleaners, and they would put it in this big washing machine, and instead of water and detergent, they'd shoot carbon tetrachloride in there. And it would do a very good job of cleaning. But the OSHA, Occupational Safety and Health Administration, and the EPA decided that we're going to have to do away with that one because the dry cleaning industry, the workers were becoming sick, and they traced the problem to carbon tetrachloride. So they had to find a different solvent, and a more expensive one, as it turns out. Anyway, they used carbon tetrachloride to clean your clothes because the soiling of your clothes is primarily oil-based. In other words, picking up oil from your environment, from your sweat, right? The water evaporates and leaves oil behind. So most of the dirt load in your clothes comes from oil. And water will not dissolve it. Okay? So this one is will not dissolve. How about these others? Well, ammonia, as it turns out, is similar to carbon tetrachloride, right? Except it has a lone pair of electrons up here, which adds to the electron density on that side of the molecule. So this molecule is polar. So it will dissolve in water. In fact, it reacts with water. Here we have methanol, wood alcohol. That's the one you don't drink unless you want to become blind. It has that OH group on the end, which makes for a polar, the potential for a polar, actually a hydrogen bonding environment. So this one is very soluble in water. How about N2 mixed with methane? Both of these are non-polar molecules. Methane has the same structure as carbon tetrachloride. It's a tetrahedron, and it's non-polar. And they're both gases. So you can argue it from either the gas side or from the polarity side. They're both non-polar, so they will dissolve in one another. But they're also both gases. And like I said earlier, all gases form homogeneous mixtures, solutions. So in that case, it doesn't matter what the gas is. The gas could be polar for all we know. The reason they form solutions so well is because they basically don't interact. There's lots of room in gas, lots of space, plenty of room for everybody. So you can put just about anything in a gaseous mixture, and it'll become a solution. All right. We usually, for convenience sake, we describe the interaction of a solute and a solvent as either soluble or insoluble. And that's the way we've been treating them up to this point. But as I've said before, nature does what it does, and we just try to explain it. And what actually happens in nature is that the solubility of a solute is on a continuum. And usually, when we say something is insoluble, it really may be only slightly soluble, which we term as insoluble. And in fact, the solubility of most liquids and solids in another solvent increases with temperature. And the reason I'm prefacing my statement with that is, if you've ever seen old equipment or an automobile engine steam cleaned, in other words, it got this long wand and you have to hold it with gauntlet gloves and use protection and steam clean it, what you're doing is you're removing the oils from the surface of the metal. Now, some of that is from the impact of the steam that comes out of that nozzle at very high speed under high pressure. But a large part of the removal of the oil from the engine is that it dissolves in the water. And it does so because oil is more soluble in high temperature water. And the steam, actually, before the steam condenses, it's a gas. So if you can turn from the heat, if you can turn the oil into a gas, then sure. I mean, it's going to go into solution because gases are all soluble. But all you need for it to do is be soluble long enough to get it off the engine. And then it ends up on the ground in a mess. And you have to clean that up, of course. But what I'm getting at is solubility of a solute can be limited to the point that we consider it insoluble. And we have terms to describe the solubility of solutes in their solvents. If we have the maximum amount of solute in a solvent that it will hold, it won't hold anymore at that temperature, then we say the solution is saturated. I make a saturated solution of sodium chloride. Right? We normally think of sodium chloride as just you put salt in water and it doesn't matter how much you put in there. But you can reach a point where the water will not hold anymore. And at that point, it's saturated. And how do I know it's saturated? In my container, I've got this sodium chloride in aqueous solution, but down here, I have solid sodium chloride sitting on the bottom of my container. And when that happens, I know that this solution is saturated because there's plenty here that could go into solution, but the solution's got all it can handle. So that's how I know it's saturated. Now, if there's none of this down here, then I know it's unsaturated. Well, actually, it could be saturated right on the edge of saturation. But if we have a lot less solute than will saturate the solution, then it's said to be unsaturated. Now, there are situations where you can supersaturate a solution. Some solutes are better at it than others. But if you raise the temperature, right, raise the temperature of this, and that solid goes into solution at higher temperature, now it's unsaturated. And then you set it on the counter gently, and don't disturb it as it cools. And when it reaches room temperature, it may still have everything in solution. And at a certain point, it has more solute than you would normally expect to see dissolved in that solvent at that temperature. How do you know it's supersaturated? All you have to do is disturb it. Shake it, or take a spatula, go on the inside of your glass and scratch it, place for the solid to accumulate. And if solid comes out of solution after that process, shaking it or whatever, then you know it was supersaturated before. And once you've disturbed it, that extra solid will come out of solution, and it won't stop until the solution is saturated. Okay, now that's an understatement. Supersaturated solutions are unstable. In fact, I think we saw a video of that British fellow in his red coat showing us phases in chemical reactions. And he had this solution that he poured into a petri dish, and there were some crystals of, I think it was ammonium acetate, crystals of ammonium acetate at the bottom, and the solution was supersaturated. So when he poured it on there, the crystals in there caused it to, the extra to come out of solution. And he built a spire out of ammonium acetate. Okay, yes, solutions are mixtures, and the amount of the solute in the mixture can vary. We need a way to quantify it, to say how much solute is in the mixture. We've just talked about the qualitative definitions, right? Where we had saturated, unsaturated, supersaturated. Other terms may also apply. We can say the solution is concentrated. That is, it has a very large amount of solute in it. And that's relative to its saturation point. It has a very large amount of solute, but not quite saturated yet. We can say the solution is concentrated. If it's a very low amount of solute, far away from saturation, we say that solution is dilute, where it's mostly solvent. Okay, these are some expressions for quantifying the concentration. How much solute is in our solvent? And we need to know amounts of both, right? They're ratioed to one another. So this is one way, the mass percent. You say, what's the mass of your solute? And ratio that to the mass of the solution. Now remember that the mass of the solution also includes the mass of the solute. They're in there together. So this is the part that's the solute, and this is the part that's the solute plus the solvent. And that's what we're illustrating here. And of course, the mass has to be in the same unit of measure. You can't put kilograms up here and grams down here, or vice versa. It doesn't work that way. So what's the mass percent of glucose in water when we have 5.5 grams of glucose and 78.2 grams of water? Well, 5.5 grams of water or glucose is in the numerator. But in the denominator, you need 5.5 plus 78.2 grams times 100. And that will give you your mass percent concentration. As it turns out, this is 6.6%. Now, what does percent mean? Remember, percent means parts per 100. Parts per 100 means it's a dimensionless number. And the only way we know what the dimensions are is we know how the number was calculated. Grams versus grams. So this is often reported as 6.6%, either mass to mass ratio, or they might say by mass, to indicate what that percent means. If they don't, and you don't know how the solution that this mixture was made, then you don't know how to interpret that 6.6%. All right. Another way, in fact, this is the more common way in chemistry to describe the concentration of a solute in its solvent. Molarity. Molarity is a formula. Big M stands for molarity, and once we decide what molarity is, there'll be a number in front of this big M. We can use big M because there are no elements in the periodic table that are just one big M. So there's no danger of confusing this with an element if we write it in a sentence. And this is the ratio of moles of solute per liter of solution. That little n is my abbreviation for moles. Moles of solute per volume in liters. Now, what does that mean? That means when you have a container here, if it's 1 liter of solution, the volume is occupied by the solute and the solvent. Okay? So when you pull out a certain amount of that, you have both solute and solvent. Okay. So since it's a formula, if we know 2 of these values, we can solve for the third one. Because that makes just one unknown. Any equation with only one unknown left can be solved. So if we write it like this, right, there's your formula. If we know the volume and we know the molarity, we can find out how many moles there are in that volume. If we know the moles and the volume that it is put into, then we can calculate the molarity. Or if we know the molarity, we say, I need 2.5 moles of the solute. Then I know this number, I know that number, I know what volume of the solution I need to acquire in order to possess 2.5 moles. It's like any formula, any mathematical formula. All right. If we have 1 mole of sugar and 125 milliliters of solution, what's the concentration? The purpose of this exercise is to drive home the point that units of measure do matter. If we have 1 mole of sugar, right, what volume is the solution? 125 milliliters needs to be in liters, right? So 125 milliliters. To make a liter, go 1, 2, 3. 0.125 liters. And then when you divide that, and there's the unit conversion here, you get 8 molar. That's what I call a concentrated solution. After a while, you develop an intuition about concentration and the expression of the quantitative in terms of the qualitative. Right? So I would say this is a concentrated solution of sugar. What about this one? You have 500 grams of potassium phosphate, and you dissolve it in enough water to make 1.5 liters of solution. So the formula still holds. Molarity equals moles per liter. What do we have? We have 500 grams. We don't have moles. We've got to find out how many moles that represents. Right. And we have 1.5 liters. That's good. Right. We already have 1.5 liters here. Now we need to find moles. So how do you find moles from mass? When you have mass and moles in the same breath, think molar mass. So what's the molar mass of potassium phosphate? You have to be able to write the formula. Right? That's why I hammered that one so hard in the beginning. If you cannot write the formula, you can't solve this problem. Potassium, phosphate, polyatomic ion. This one has a 1+ charge because it's an alkali metal. This one has a 3- charge because it's a polyatomic ion with a fixed charge at 3-. So that means we need 3 of these. Now, what's the molar mass? 3 times potassium, 1 times phosphorus, and 4 times oxygen. Add those together. And then how do we deal with 500 grams of that product? We need the conversion factor that's derived from the molar mass. Right? We need this value right here. Okay? And here's the molar mass, 212.27 grams per mole for that formula unit. And then we convert this into 2.355 moles. That's what this is. And that goes up here. And then we can do the calculation. 1.57 molar. That simply says if you have a liter of this solution, you will have 1.57 moles of potassium phosphate in that volume. Now here's one worked in using the formula. The known value is the molarity. So this one is 10 molar. And that was crapping out on it. 10 molar. And what volume of the solution do you need to have 2 moles of sugar? There you go. Now you solve for the unknown. .2 liters, which, by the way, is how many milliliters? Well, milli says you're getting smaller in units, so the number has to get bigger. So you move to the right, 3, 2, 3. So that's 200 milliliters. Okay? How about this one? You have separate solutions of sodium hydroxide and potassium chloride, and you dissolve 100 grams each in 250 milliliters of solution. What's the concentration of each in molarity? So for this one, you've got 100 grams of each, but you don't have the same number of moles of each because they have different molar masses. So we have to go in and calculate how many moles of sodium hydroxide per units in liters of the volume. That's what these two values are doing. That turns out sodium hydroxide is 10 molar, which is extremely concentrated and dangerous. It's very corrosive. And this one for potassium chloride is fairly concentrated, but not quite as concentrated as sodium hydroxide. All right. Okay, so we have two HCl solutions. All right, remember our nomenclature? HCl. Now I'm assuming that these are aqueous solutions. They don't have to be, but for the sake of argument, if they were aqueous solutions, we'd call that hydrochloric acid. Solution A and solution B. So we have solution A and solution B. Solution A has a greater concentration than B. So the molarity of A is greater than the molarity of B. Which of the following statements is true? If you have equal volumes of both solutions, solution B must contain more moles. Okay, if you have equal volumes, all right, so what does this one mean? This one means moles of A per volume of A is greater than moles of B per volume of B. That's just what these are equal to. Since the question is equal volumes, right, we need this interpreted in terms of volume, not that one. It's a little easier to answer the question if we see it this way. So what are we saying? Equal volumes. So if these two are equal, but this one's greater than that, that means this whole term is greater than that one. So how did it get there? Right? It got there, if we have equal volumes, it got there by having more moles of A. If these are equal volumes, then A has to be bigger than B. So that's false. Solution B contains fewer than A. Right? If you have equal moles of these two, solution B has a greater volume. If these are equal, then these terms get bigger. If those are equal, they get bigger by this one, A being smaller, right? It's the quotient that matters. If this is smaller, that term gets bigger. So the volume of A is less than the volume of B if the moles are equal. Yes, B does have a greater volume. So B is true. How about C? To obtain equal concentrations of both solutions, you must add a certain amount of water to solution B. What happens if you add more solvent? The concentration goes down, correct? Because you're making this one bigger, so the whole term gets smaller, right? So C is false. If you want equal concentrations, you need to add volume to A. That makes this bigger and the term gets smaller, approaching that of B. So C is false. D, adding more moles of HCl to both solutions will make them less concentrated. No, if you increase the number of moles to both of them, it will make them more concentrated. So the only one that's true is B. All right. Okay. Now that we know how to express concentration in terms of molarity, moles per liter, that's for the whole formula unit. For instance, for our potassium phosphate. Okay, we had a certain concentration there for that. But what happens when it goes into solution? This is an ionic compound. What does it do? Right? It breaks up into potassium ions, 3 of them, right? And 1 phosphate ion. And these are in aqueous solution. Okay. How do we express that? Well, if this is, I forget the number, but let's just for argument's sake, let's say this is 1 molar. What would the molarity of potassium ions be? It would be 3 times that, wouldn't it? Right? You're making 3 out of this 1 unit. So 1 molar of that unit gives you 3 molar of potassium ions. But this is 1 for every 1. So this one is still 1 molar. What's the concentration of total ions? 1 molar of this gives you 3 plus 1 is 4 moles of these ions. So the ionic concentration is 4 molar. That's what this slide is about. Okay. Calcium chloride dissociates into 1 calcium and 2 chlorides, which means for 0.25, you've got 0.25 molar of calcium ions, but you got 0.5 molar of chloride ions. All right. Which one contains the greatest number of ions? Let's see. Trying to find a marker that works. So we've got these 4 solutions. We've got 400 milliliters of 0.1 molar sodium chloride. Okay. 300 milliliters of 0.1 molar calcium chloride. 200 milliliters of 0.1 molar iron 3 chloride. And we have 800 milliliters of 0.1 molar sucrose. Okay, which one has the greatest number of ions? Well, the first thing I want to do is be sure that we're talking about ions for every solution. Yeah, that's ionic in solution. That's ionic in solution. That doesn't make ions. Sucrose does not dissociate. So you can forget about that one. Now we need to compare these. If we're talking about absolute amounts, the expression M equals moles divided by V, the question is the greatest number of ions. We're talking about moles of ions. So we're going to solve this for moles. N equals M times V. Okay? So this is V, and this is M. Multiply them both together. Now, I know what you're thinking. We can't multiply those together because this is milliliters. All right? That's technically true based on that formula. But I'm going to show you a little trick. If you multiply molarity times milliliters, you get millimoles. Not moles, but millimoles. So if I multiply this one times that, I get 400, I get 40 millimoles. That's just 1,000th of a mole. And I'll prove to you in a minute why that works. This one will give us 30 millimoles of compound. Right? That's the formula unit. This one is 20 millimoles of the compound. But it asks us how many ions. How many ions are formed from each one of these formula units? 2. So that one's times 2. This one's times 1 plus 2 is 3. This one is 4. So 2 times it's 80. This one's 90. And this one's 80. So the greatest number of ions is formed by this solution. Now for the millimole thing. Okay. If we write this in terms of molarity, molarity is moles per liter, right? Moles per liter. Suppose this ratio then is fixed. And if we divide both of them by 1,000, what do we get? Well, if we divide this one by 1,000, we have to divide this one by 1,000 also, don't we? Right? To maintain the ratio. That's a mathematical identity. Well, what is this one? 1,000th of a liter is milliliter, right? What's 1,000th of a mole? A millimole. Okay? And it's still molarity, right? All we've done is divide this one by 1,000, that one by 1,000. So if we multiply molarity times milliliters, we get millimoles. Okay? And that saves you a step. If you have to calculate this from these terms, and that one's moles, then this one has to be liters. But if that was millimoles, you can use milliliters here based upon this argument. And that saves you time and energy. It also answers the question. Okay. Well, in this one, we did convert to liters and use moles. So this slide doesn't take advantage of that trick. But it comes up with the same answer. So when we solve these problems, we're talking about problem solution. What they're saying here, where are we going? They're actually saying, what's the question? You got to know the question or you'll never get the answer. And then how do we get there? Right? Develop a strategy for solution. And that varies depending on what the problem is. And then check yourself at the end to be sure if the answer makes sense. Okay. Now that we know how to express concentrations of our solution, it's often important to know the exact concentration of a solution, as near as we can get it. Right? Remember, anytime we do anything in sciences, there's potential for error. I think I've got a video coming up. Yes, I do have a video coming up, and it describes how to make a solution of known concentration, very accurately known concentration. It requires the use of sometimes an analytical balance. It's very accurately weigh a substance. Volumetric glassware that is calibrated to hold a certain amount of solution. And so I'll play the video, and what I'll do is actually, the video is going to be recorded, but the video is a recording being projected on a screen and then recorded again. So every time you lose quality. So what I'm going to do is, after I receive the Zoom sends me the file, I'm going to go in and edit out this video and put in the original, so it'll be a higher quality. That'll take a little bit longer, but not too bad. But for now, just watch the video and you'll see how to prepare accurately a solution of known concentration. Let's see. I guess I have to start.
Hi, I'm Jared Hyman, an assistant professor of chemistry at Elon University. Today, I'll be taking you through the appropriate technique and procedure for preparing a chemical solution. One of the most important abilities at all levels of chemistry is the preparing of a solution of a specific concentration. First, we'll define some of the terms used in this process. A solution is a homogeneous mixture of two or more chemicals. For the simplest solution, a smaller amount of one chemical, called the solute, is placed in a larger amount of a second chemical, known as the solvent. Today, we will be preparing a solution of sodium chloride, using a small amount of sodium chloride as our solute, added to a larger volume of water, our solvent. Before beginning any experiment, it's important to observe appropriate lab safety procedure and know the hazards of any chemicals you're working with. In any chemical reaction, it's important to keep track of the exact amount of reactants present, and for stoichiometric purposes, we use the term mole to define the amount of a substance. A mole is a counting term, similar to a dozen eggs, where 1 mole is equal to 6.022 times 10 to the 23rd things. As you can see, this is a really large number. The periodic table uses molar counting as a means of converting to a more experimental term of mass. For example, 1 mole of carbon atoms has a mass of 12.01 grams. In a compound such as sodium chloride, it's made up of 1 mole of sodium atoms with a mass of 22.98 grams per mole, along with 1 mole of chlorine atoms with a mass of 35.45 grams per mole, giving us a total of 58.43 grams per mole of sodium chloride. This means of using mass to determine the amount of a substance is useful for pure chemicals. But in the case of solutions, we now have a mixture of multiple different substances. Therefore, we express amount as a concentration. The most common unit for concentration in chemistry is molarity, abbreviated capital M, which indicates the number of moles of solute dissolved in a certain volume of the total solution. This gives molarity derived units of moles per liter. It is very important to note that this is a volume of solution, not the volume of solvent. Today, we will be preparing 500 milliliters of a 0.25 molar sodium chloride solution. Before beginning, it's important to map out your procedure for preparing this solution. Here, we'll look at the amount of sodium chloride we need in this solution. We know that we want to prepare a 0.25 molar solution, which means that there is 0.25 moles per liter of solution. We also know that we only want 500 milliliters of this solution, or a half liter. If we multiply these two terms together, we can see that we will need 0.125 moles of sodium chloride. From earlier, we can remember that there are 58.43 grams per mole of sodium chloride. We can determine that the exact mass that must be measured out is 7.304 grams of sodium chloride. In lab, obtain some sodium chloride in a clean lab scoop, and using a balance with some weighing paper, measure out as close to 7.304 grams as possible, marking down your exact mass. Note that if you go over the desired mass, it's never appropriate laboratory procedure to put the excess reagent back into the original container. Always use an additional container to collect the excess. Once you've measured out your solid and recorded the exact mass, transfer all of the solid to the appropriate sized volumetric flask. Volumetric flasks are made specifically for this purpose and should be used over other less accurate labware, such as beakers, Erlenmeyer flasks, or graduated cylinders. Here, we just transferred our solute to the 500 milliliter volumetric flask. If any solute remains on the weighing paper, use a spatula or a small amount of water to transfer the remaining salt. Next, add enough water so that the bulb area at the bottom of the flask is approximately half full. This will give you enough room to swirl the liquid, allowing the solute to completely dissolve. Again, it's critical that all of the solute is dissolved prior to filling to the appropriate volume, as different solutes may take up more volume in solution than their undissolved salts. Now that the sodium chloride is completely dissolved, we can fill the rest of the bulb area and some of the neck with water. You should now carefully and slowly add water, our solvent, as it begins to fill the neck. Once you approach the etched or printed line on the neck of the flask, you should add solvent dropwise, monitoring the location of the meniscus. Water, as a polar solvent, tends to cling to the glass walls of a flask. This phenomenon creates what is called a meniscus. The bottom of this curved meniscus should sit directly level with the line on the flask. At this point, there is exactly 500 milliliters of solution with an air of 0.2 milliliters. Different volume flasks have different air values. However, the air on a volumetric flask is much lower than any other type of glassware of similar volume. For example, the volume markings on a beaker or an Erlenmeyer flask are only accurate to plus or minus 5%, meaning if the meniscus were on the 500 milliliter line, it could be anywhere between 475 milliliters and 525 milliliters. On the other hand, using a volumetric flask, we know that the volume is exactly somewhere between 499.8 milliliters and 500.2 milliliters, meaning it's much more accurate. We now must determine the exact concentration of our solution by taking the mass that we measured out and dividing by formula mass for sodium chloride, 58.43 grams per mole, which gives us a total number of moles in our solution of 0.1253 moles. We can then take this number and divide by our volume of 0.5000 liters to give us a total exact concentration of this solution of 0.2501 molar sodium chloride. This value and the contents of the solution should be clearly labeled on the chosen storage container for laboratory safety protocol. You've now learned how to make a solution from a solid. Everything you need to do this demonstration in your lab is available from Carolina. We have experts who can assist you with any of your science demonstration needs. Visit us at carolinachemistry.com to see our complete line of products and kits for chemistry.
Okay. All right, so this is what he did in short. Is he weighed out the solute, transferred it to a volumetric flask, dissolved part of it, dissolved all of the solute in about half the water that he needed. And then he brought the volume up to the mark. Let me check something. Okay. I'm not sure what this is about. Okay. So before you add enough water to bring your solution to the mark, everything needs to be in solution. Because when the solute goes into those holes that we talked about earlier, sometimes they don't take up as much space as was there before. So they make the solution smaller than it would be, or they take up more space and expand. So the presence of the solute changes the volume of the solvent. So what could possibly go wrong with this procedure? Well, there's several things. You could make an error in weighing, or you could not transfer all of the solid into your flask. That would be an error. If you don't wait for the solute to be completely dissolved, that could introduce an error also. You could add add solvent up to the mark, but miss the mark. In other words, you read it wrong. Say you read it at the top of the meniscus rather than the bottom of the meniscus. This volumetric glassware is calibrated for aqueous solutions. So you always read the bottom of the meniscus. Or you could overshoot it, by accident. What if the mixing process, like we mentioned earlier, generates a lot of heat, or or absorbs heat? It gets cold versus hot. That could introduce an error if you don't do the dilution at room temperature. Volumetric glassware is calibrated for aqueous solutions at 25 degrees, usually, unless it says on the flask a different value, then you assume 25 degrees. So at room temperature, between 20 and 25 degrees, the error is not significant. But if it's very hot or very cold, you do get a change in volume of your solution. And that could introduce error also. There may be other forms of error that could be. Your sodium chloride, in this case, your solute, could be contaminated. You think you're weighing out 5 grams, but you're really only weighing out 4.8 grams because it's contaminated. It's got something else in there. That's a possibility. Okay. So once you have a solution, maybe the solution has the materials in it that you want, solvent and solute, but they're the wrong concentration. If they're a higher concentration than you need, then you can dilute, add some more solvent, and arrive at the proper concentration. So here's how dilution works. When you've got, let's see, do I have an animation on this one? No. Okay. When you have a solution over here of a certain molarity, let's say this is a concentrated molarity, and you want a solution over here, in this one to be your diluted concentration. If you take some of this one out here, put it in there, and add solvent to the mark, then you have diluted it. But we need to know exactly the concentration of this one based on what we did in that process. So you're going to take a volume out of here. Right? You're going to take a certain volume of the concentrated one, put it in here, and now your new volume is the volume of the flask. Okay? All right, so how many moles did we take out of here? Remember, molarity equals moles divided by volume. Right, so moles will be equal to molarity times volume. So the moles we took out of here will be equal to the moles taken out of the concentrated side would be molarity times the volume that we extracted. And that has to be accurate also. We use volumetric pipettes usually to draw out an exact volume of the concentrated. Okay? So we're transferring moles here over to moles here. Now, what do these two have in common? In the process of transferring those moles, assuming you don't spill any, you have the exact same number of moles coming out of here that you have going in there. And the moles here, the total moles in here, is equal to the volume times the molarity. Okay? But these two are equal, right? So those terms are both equal. That's mathematical identity. So the molarity times the volume of the concentrated equals the molarity times the volume of the diluted. That's why dilution works. And this is like any other formula. If you know three of those, you can determine the fourth one. Say you know the concentration of your concentrated solution, and you know the volume of your container, the final volume, and you know the molarity that you want to have of the diluted solution. Then you can solve for how much volume do I need to extract from the concentrated and dilute in order to have that molarity. That's why this works. Here it's M1V1 equals M2V2. That's concentrated and dilute. And they both, and this formula works because moles equals moles. Now, we can use our trick when we analyze and use these formulas, because molarity times volume, if the volume is in milliliters here, then it's going to be in milliliters here. So we don't have to change milliliters to liters to use this formula. Oh, we got another video.
Hi, I'm Jared Hyman, an assistant professor of chemistry at Elon University. Today I'll be taking you through the appropriate procedure and technique for diluting a solution. A common laboratory technique is preparing a more dilute solution from a concentrated stock solution. In this case, we are going to prepare a 0.250 liter solution of 0.01 molar. We know our stock solution has a concentration of 0.250 molar. The first thing we need to do is determine the exact number of moles in our dilute solution. We know our concentration needs to be 0.01 molar or 0.01 moles per liter. Since we know our number of moles per liter and we know the volume we need, we can calculate that we need exactly 0.0025 moles of sodium chloride. Knowing our stock solution contains 0.25 moles per liter, we can take the number of moles needed in our dilute solution and divide by the concentration of our stock solution to calculate the exact number of milliliters that must be transferred into our new solution. In this case, 0.01 liters of sodium chloride solution, or 10 milliliters. This is the stock solution of sodium chloride that we will be diluting. Make sure to pour the stock solution into another container before inserting the pipette into the solution. This is because you do not want to contaminate your stock solution. In this case, I'm using an Erlenmeyer flask. Notice that I have clearly labeled the flasks to adhere to proper laboratory safety protocol. To prepare our dilute solution, we will take a 10 milliliter aliquot of our stock solution using a 10 milliliter volumetric pipette. To use the pipette, place the pipette in the liquid to be collected. Squeeze the pipette bulb and allow the liquid to rise up the pipette. You should allow the liquid to pass the line marked on the pipette, but before the bulb. Remove the bulb and place your other thumb over the end, creating a seal, and slowly release just the corner of your thumb, allowing the liquid to exit so that the meniscus is directly on the line marked on the pipette. This takes some practice, and you may need to use the bulb to pull more liquid into the pipette again. Never pipette by mouth. Once you have the exact amount of liquid required in the pipette, hold your thumb firmly over the end and transfer the pipette to a new volumetric flask, in this case a clean 250 milliliter volumetric flask. Allow all of the liquid to flow out of the pipette. Do not use the bulb to force the liquid out, as pipettes are designed to deliver the exact amount of liquid, and there may be a small amount of liquid remaining at the end. Remove the pipette and follow the same procedure as before, filling the volumetric flask with solvent, again monitoring the meniscus until the exact volume is reached. You've now learned how to prepare a dilute solution from a stock solution. To see how to prepare a stock solution, you can view our solution preparation video at carolina.com/video. Everything you need to perform this technique in your lab is available from Carolina. Visit us at carolinachemistry.com to see our complete line of products and kits for chemistry.
Okay. I noticed one mistake that he made. It's not a major mistake, but if you're trying for accuracy, then we'll need to take note of it. When you fill your pipette, you've got the bulb on it and you're pulling the solution up. It goes above the mark and you seal it with your finger. Then you take it out of the container and you use a chem wipe and you wipe down the outside, because you don't want any outside liquid to be transferred as well. So you clean the outside with just a simple wipe. Then you go back over the container that you drew it out of, and you rock your finger a little bit, and that'll allow air to be metered in and drop the line to the line on your pipette. Then once that happens, you just touch the inside, touch the tip of the pipette to the inside of your container to remove any hanging drops. Now you're ready to transfer. And from there, it's good. Just the way he described it. Okay. So we're kind of running short on time. I only got 5 minutes and I got other subjects to cover. So we're going to have to skip these concept checks. I'll put them up here and pause for a second so that the information is there on the recording, but I'm not going to discuss it. This is a dilution problem. Okay. In fact, I like this single equation version better than the one described in the video. They separate out the parts. This part they separate from that part. Actually, do this part first, and then they go back to that part, which is true, but I don't like to separate those things. I think they're better understood if they occur in an equation. And we solve for the answer to the question. Okay, now we're coming to stoichiometry. Remember when we discussed stoichiometry earlier, it was in terms of a balanced equation first, and then masses of reactants or products. And remember, we had to convert mass to moles before we could move anywhere in that equation. Right? Same concept here, only now we're not working from mass, we're working from concentrations of solutions. But you still have to know moles before you can move in the equation. So that's the key. In the solution chemistry, you use the concentrations and the volumes delivered in order to determine moles. Okay, so let's see. Let me check my hard copy on this one. Part 1. Okay. This one's going to make a point of the fact that many solution reactions produce solids. You get two solutions that are clear. You can see through them. You can shine a light through them. You don't see any. In fact, let me make a point of that. How do you know you have a solution? If this is a clear beaker and you have a flashlight over here, right? And it shines a light and it comes out over here and you can see it on this side. You can see the light coming out on that side. Well, if you look in from right angles, if it's a solution, you cannot see the beam of light in here. That's a solution. If it's a suspension, if you have fine particles in there and you think you have a solution, shine a light through it. If you can see the beam in there, that means you do not have a solution. This is called the Tyndall effect. Okay, so we know we have two solutions that we're going to put together. And when we do that, sometimes those ions that break apart, they recombine into compounds that are not soluble. If they're not soluble, then when you put the solutions together, they form usually a cloudy, sometimes colored suspension. And over time, it settles out. So they form a solid. That's called precipitation. So when we put two solutions together, sometimes we may or may not expect a precipitation. In this case, we've got these two solutions, sodium phosphate and lead 2 nitrate. This is how many milliliters of the sodium phosphate of that concentration, and this is 20 milliliters of 0.2 molar lead 2 nitrate solution. These are aqueous solutions, obviously. And when you combine them, the question is, what precipitate forms? Does a precipitate form? Look at it this way. What is sodium phosphate? Sodium phosphate, right? +1 charge, -3 charge. This is aqueous solution. And then we're going to add lead 2 nitrate. So that's a 2+, and nitrate is a 1-, so this has a 2. And this is an aqueous solution. Okay? What did we say about ionic compounds in solution? They break up into the individual ions. Right? So this one's going to be sodium ions, this one's going to be phosphate ions, this will be nitrate ions, and that will be lead 2+ ions. how do we know that there's going to be a solid formed? This is known as a double replacement reaction. This one swaps places with that one. And then you see what's the nature of the compound that forms. The other way to do it is you take all your cations, put them across the top, and form a grid. And we have phosphate here and nitrate here. Okay? Those are the possible combinations, right? Sodium phosphate, we know that one is soluble because it's already in solution. Lead 2 nitrate, we know that one is soluble because that's the way it was when we put it in solution. The question is, lead and phosphate, when they combine, do they form that solid that drops out of solution? Or sodium and nitrate, do they do that? You need, let's see, have we already done that? Have we done double replacement reactions? We must have. Did I give you guys a chart to show solubility? Yeah. Yeah, that was last, that was chapter 9. Okay. So you take that chart that I gave you and you look at combinations of sodium and nitrate. You find out that that chart tells you they're soluble. But when you combine lead 2 plus and phosphate, we find that it's insoluble. So the precipitate that forms in this case, well, it didn't give it. The precipitate that forms is lead phosphate, lead 2 plus phosphate. So in order to balance that, we need a 3 over here and a 2 over there. And that'll give you 6 minuses and 6 pluses. So this is the solid that forms. And the sodium nitrate is still in solution. Okay? What's the mass of the precipitate that will form? Well, in order to do that, we need to use stoichiometry. And I'm out of time, so if you have to go, go ahead. I'll just keep recording. So remember, we have to make moles. First, we have to balance the equation. Let me see if we're going to do that. Hard copy. Yes. Yes, we will do that. Okay, we found out what the precipitate was. Okay. There we have aqueous. Sodium nitrate is still in solution, and lead 2 phosphate is our solid. Then how do we find the mass? What we have to do next is balance the equation. And the equation has been balanced for us here. Right? Coefficient of 2, 3, 6, and 1. And we did that using the budget method. And since the phosphate is the same on this side as it is on that side, and the nitrate's the same as on both sides, we can use those polyatomic ions as balancing units. You don't have to break them up into elements. And once we use the budgeting method, we get these coefficients for our balanced equation. Now what we have to do is find out since we're given absolute amounts of both reactants, one of them is limited. So we have to find out how many moles of sodium phosphate are in that solution, in this volume times the concentration, just like our definition tells us, gives us this many moles of sodium phosphate. And then we do the same thing for lead 2 phosphate. So we have that many moles of lead 2 phosphate. Now, remember how we found the limiting reactant? You convert, you say, convert all of this, since it's now in moles, we can move in our equation, convert all of this into that, into the solid. Say, how much solid does it form? And then do the same thing for the lead 2 nitrate. How much solid does it form? And the limiting one is the one that makes the least amount. And that's good because the next question is, how much of that is there? Right? So when we do that conversion, we find that the sodium phosphate has the potential to make 0.0015 moles of the precipitate. If we do that same conversion for the other reactant, we find that it makes 0.00133 moles. It makes less. So this is the limiting reactant right there. The lead 2 nitrate is limiting, and it will only form this amount of the precipitate. So now we just need to convert that to mass. Use the molar mass of lead 2 phosphate. Here we go. Here we go. There we go. We take the limiting reactant and what it forms and convert that to 1.08 grams of the precipitate. That's stoichiometry of solutions. This question wants to know, what's the concentration of nitrate ions in the final mixture? Remember, nitrate is soluble here and it's soluble there. It's a spectator. It does not precipitate. It's in solution before, it's in solution after. The only thing that changes is the volume. In this one, it was only in 20 milliliters. And this is 10 milliliters. So now the volume is the same number of moles of nitrate, but now we're in 30 milliliters. Total volume. That's the key to this problem. So here's our balanced equation again. Nitrate spectators. So if we have 0.0040 moles of lead 2 nitrate at the beginning, how many moles of nitrate do we have at the beginning? Remember our ratios. We have that many moles of lead, but we have twice that many moles of nitrate. So we actually have 0.0080 moles of nitrate. Now that's 80 moles. Actually, 0.030 liters. And then 0.0080 moles of nitrate. And that will give us the concentration of nitrate. 8.27 molar of nitrate. This one wants to know what's the concentration of phosphate ions left over. Now in that case, we've used up some of the phosphate. Okay, which one was our limiting reactant? It was this one, the limiting reactant. So we did not use up all of our phosphate. We're going to have some phosphate left over. What we have to do is decide how much of that phosphate was used and subtract it from the starting amount. That gives us the moles of phosphate left over, and then we divide it by our new volume. So here we have our equation again. In this case, we're simplifying it to the net ionic reaction. Right? We got rid of the spectators. Okay, we have this much sodium phosphate to begin with, 0.0030 moles of this compound, which means since there's only one phosphate per, that means we have that many moles to start with of phosphate. Now we need to see how many moles were actually used. Okay. So if we know that we have this many moles of lead to begin with, then this converts 3 moles of lead to 2 moles of phosphate. That's how many moles were used in the reaction, right? Based upon this proportion. Okay. So now, if we use that many, and this is how we start with, this is how many moles we have left over. So we just divide that by our volume. And our concentration of phosphate in solution now is 0.01 molar. Very low. Oops. Okay. Another type of reaction that occurs in solutions is acid-base. Often called a neutralization reaction. And in this case, the net ionic equation for an acid-base reaction is hydrogen ions plus hydroxyls yields water. Let me be sure we've covered that already. That's chapter 16. We haven't covered acids and bases yet. All right, so this is going to be a bit strange. This means an acid, this means a base. When you put them together, you always get water. But if we approach it stoichiometrically, just like any other reaction, you have this compound. For that example, you have this compound plus this compound, and it yields, it's a double replacement. You swap this one for that one. So sodium and sulfate get together. And hydrogen and hydroxyl get together. Okay? And then you balance the equation. Right? We actually have 2 hydrogens here and 1 there. So actually we need 2 of these and 2 of these. That should balance it. 2 sodiums, 1 sulfate, 1, 2, 3, 4 oxygens, 4 hydrogens, 4 hydrogens, and 2 oxygens. So now we're balanced. And this is all in solution. This is an aqueous solution. This is aqueous. This is aqueous. You know, look it up in your chart and you'll find that this is soluble. And this is a pure liquid. Okay? So if we know the concentration and how many milliliters, we can say how many moles of this participate in the reaction and how many moles of that participate and find out the limiting reactant if necessary. So when we do that, we find that it takes twice as many moles of sodium hydroxide to react with a mole of sulfuric acid. And the reason for that is this produces 1 hydroxyl per molecule, and this produces 2 hydrogens. And the point of that previous slide was this is how they react. Right? One hydrogen needs one hydroxyl. But if you have two hydrogens, you need two hydroxyls. So that's where that comes from. We can approach this as a simple stoichiometric problem. In this case, how many moles of sodium hydroxide are required? So the question is, how many moles of sodium hydroxide are required to react with 1 liter of 0.5 molar? Right? We have to find moles. Molarity times volume equals moles. So that's 0.500 moles of that compound. But for each one of these, it takes 2 of those. So that means we need 1 mole of sodium hydroxide. There you go, your balanced equation. Wait a minute. We're missing a coefficient there. That's an error. We'll make a note and fix that. Okay. Yeah, that's an error. Fortunately, it won't affect our calculation because this ratio is correct, 2 to 1. And there's our conversion factor for this, gives us 1 mole of sodium hydroxide. Okay. For people that work with acids and bases a lot, day in and day out, they find it more useful to try to level the playing field, so to speak. With this playing field, the sulfuric acid is twice as valuable as sodium hydroxide because it makes 2 protons for each unit, whereas sodium hydroxide only makes 1 hydroxyl. So they invented a new unit of measure called the equivalent. 1 equivalent of acid is however much acid it takes to furnish 1 mole of hydrogen ions. So actually, 1 mole of H2SO4 makes 2 equivalents of hydrogen ions. So a half a mole would be the equivalent acid. 1 equivalent of H2SO4 is 0.5 moles because it makes 1 mole of hydrogen ions. Same for the base, except this is in terms of hydroxyls. So sodium hydroxide makes 1 hydroxyl per formula unit, which means 1 mole is 1 equivalent. The equivalent weight is the mass of that's required to make 1 equivalent of an acid or a base. So that would be the molar mass for this one. What's the molar mass of sodium hydroxide? Because it's 1 equivalent per mole. So the molar mass of that would be the equivalent weight. But for this one, since sulfuric acid makes 2 hydrogens for each mole, then its equivalent weight would be half of its molar mass. And that's what this slide is supposed to illustrate. Here we have the molar mass of hydrochloric acid is 36.5 and its equivalent weight is 36.5. Same for nitric acid. It's all based upon how many hydrogens they produce. Whereas H2SO4 has a molar mass of 98, but an equivalent weight of 49. So 49 grams of H2SO4 is equal to 1 equivalent, or it makes 1 mole of hydrogen ions. Okay. Now that we know what an equivalent is, our new unit of concentration, instead of molarity, we call it normality. Okay? 1 N, 1 normality, one normal is the number of equivalents per liter. So instead of moles here, we say equivalents. And equivalence is relative to the number of hydrogen ions, number of hydroxyl ions. And that's per liter, just like before, just like molarity. Now, when we say that, then we can say that when we react an acid and a base to find out where they are equal, and they consume all of the acid and base and make these products, that's known as the stoichiometric mixture. Remember? The stoichiometric mixture, now we can do the calculation as NV equals NV. This is for the acid, this is for the base. Okay? If this were hydrochloric acid, then MAVA equals MBVB would be equally valid because they're 1 to 1. But when there are different numbers of protons than hydroxyls in the reaction, then normality is the equation that works. Okay, so how many equivalents of barium hydroxide are there in 4 moles of barium hydroxide? We make 2 hydroxyls each. So instead of 4 moles, now we have 8 equivalents. That's how much barium hydroxide we have here. 8 equivalents is 4 moles. Okay, that's it for chapter 15. And next, let's see, it's Tuesday, Thursday, we'll do a review on this using the review document that you'll find in the Blackboard. We'll work some problems.